Hey everyone, welcome to week 3 of Building Service Systems. I hope you all had a great weekend and are ready to dive back into some energy content. So let's look at what we're going to do this week. So the focus this week is on heat movement, uh, in particular thermal energy, and how it's transported through building surfaces. This is a very, very, very important consideration for managing systems in a building and managing the temperature of a building. And so, just to make sure, in case you're not aware, we do provide this overview every week that gives you sort of a little bit of an introduction, some key questions that you'll answer this week, or you'll be able to answer this week. Excuse me. And then, of course, your content. So is some book reading to be done. And then there's also our usual D2L readings and videos and so forth. We also list what's due that week. So this is a good extra sort of heads up on what you need to get done. Okay, so what are we talking about this week? I'm not going to go over too much detail because all of this obviously is here. Um, but the main thing this lesson focuses on is how heat travels through surfaces. So heat travels, it's going to go through a surface. You can't stop it. It's going to flow through. Now you can slow it down by adding insulation, which I'm sure you know, but you can't stop it. And so this first part of the lesson kind of goes over the basic physics of it and how heat actually travels through surfaces. Um, and then U value and R value, just see the ed puzzles below. So this is really important. This is going to come up a lot in your lab this week. So most people are familiar with R value, which is the thermal resistance. So it's basically a measure of the insulation level. That's how we're used to thinking of it. U value is not as intuitive because with R value, the bigger the R value, the better the insulation, or the higher the insulating value. But since the U value is the inverse of R value, so it's 1 over R, and R is also 1 over U. But since U equals 1 over R, if you think about it, as the R value goes up, the U value is going to go down. And so you actually want to really low U value. And R value is resistance, and U value is transmit. So it's how U value technically is how many BTUs will travel through a square foot of a surface, right? Imagine a square foot of wall or ceiling or whatever. You take a square foot of that, how many BTUs will travel through that square foot over the course of 1 hour for every degree Fahrenheit difference between the two sides. And so heat will always, and I underline always, travel from warmer to colder. So if you have a warmer side of a wall, then it's going to travel from the warmer side to the colder side. So during the cooling season, so in the summer, heat is going from the outside to the inside, assuming that it's colder inside than outside. And then obviously the opposite is true in the winter. Now, if there is no delta T, so I kind of lied at the beginning, you can stop heat flow. The only way really to stop it is if there's no delta T. So delta T means the temperature difference. And so if there's no temperature difference on either side of a surface, then heat will not flow. It's really difficult to get an exact, um, the exact same temperature, but theoretically, if that's the case, there will be no heat flow. And so it follows that heat is going to flow through a surface until the temperatures are equal. So this is a theme that's going to come up kind of a couple of times throughout the semester, and that is that nature kind of tends toward equilibrium. It's really hard to achieve it, but it tends toward equilibrium, meaning if you have a temperature difference, the heat's going to flow until there is no temperature difference. If you have a pressure difference, air is going to flow until there's no pressure difference. And we'll go over that more next week. Okay, so that's a principle, fundamental principle of heat flow, excuse me. Um, then with heating degree days, we'll use this in lab, but it's basically a measure of how much heating is needed throughout a typical heating season in a climate. So this is based on your location. Every location has its own heating degree days or HDD. And so this value is pretty easy to find, and you'll use it in your lab this week. And so the higher the HDD, that means the colder the climate because you need more heating. So higher HDD means you need more heating. So in like North Dakota, you need like HDDs are like a 10,000. In Florida, it's around 1,000, right? So 10,000 where it's really cold and 1,000 where it's warm. And then we're not going to really talk about cooling degree days much this week, but CDD is the opposite, right? So the more cooling energy you need, the higher your CDD. I'm going to go over the basic physics of insulation, how insulation works. Here's the secret. It's air pockets. It's all about air. Okay, so more air pockets, um, generally speaking, means better insulation. And that's how insulation really works. It's all about the air pockets. And so if you don't have air pockets like solid metal or solid wood, um, then heat travels through that pretty readily. And then finally, we're going to go over some efficiency calculations. These are really important when you're determining the input of um, in particular furnaces, but it kind of works for cooling as well. But we'll talk about the efficiency rating for cooling systems later. But this is really important. Um, this relationship that efficiency equals output over input. Um, so if you want to know the efficiency of a furnace, if you look at the BTUs of input, excuse me, BTUs of output, you divide that by the BTUs of input. That's your efficiency. And it makes sense if you think about it. If half of the BTUs that you put in end up going out, then it's about 50% efficient, right? So it's pretty logical. And then you can just do some basic algebraic rearrangement, and then output is efficiency times input. This is really helpful. If you know the efficiency of a furnace and you know the input, then you can just multiply those together and you can get your output. This is something we talked about last week when I mentioned that the BTU rating of a furnace, if you remember this, the BTU rating is actually the input rating. And so you have a 100 MBH furnace, which is 100,000 BTUs per hour. And if it's 80% efficient, then you multiply those two numbers together, and that'll tell you your output. And then finally, if we want to know our input, this is really helpful um, if we know how much heat we need over the course of a season or any period of time. So that's our output necessary. So that's actually what you calculate in this week's lab when you calculate a heating load. It's called a heating load, which is the heating demand over the course of one heating season. And so you'll calculate that in BTUs, and that is the output, the BTUs of output you need to sufficiently heat whatever space that is over the course of one heating season. And so you calculate the output, which is your heating load, and then if you know the efficiency of your furnace, then all you need to do is take that output, which is again how much heat in BTUs I need to provide all the heat for my space, and then I divide that by the efficiency, and that'll tell me how many BTUs of input I need to provide that output. Okay, and so then I know my BTUs of input, and I can easily now, as can you, convert that to whatever my heating source is. So if I'm heating with fuel oil, and I know my total BTUs of input that I need to heat that building or that space over the course of the entire heating season, then I just have to convert that to gallons of heating oil, which would be dividing by 139,000 BTUs. Okay, so that's actually something that you will do in lab this week. You will calculate the output necessary to replace the heat that's lost through a surface. And then you're going to apply an efficiency assumption to calculate the BTUs of input and ultimately the CCS of natural gas you need. And so you'll also see what happens when you increase the efficiency. And I think that it's logical. I'm sure you can, if I ask you, if I have a more efficient furnace, would I need less heating input to heat a space? And of course the answer is yes. If it's more efficient, that means I'm getting sort of more bang for my buck. And so mathematically what that means is you're dividing by a higher decimal, right? So if it's 95% efficient instead of 80% efficient, then your input's going to be less. Okay, so you'll work through the math this week. Okay, so that's a kind of a high level overview of what you're going to go over this week. So ultimately, what you will be able to do by the end of the week is explain how heat transfers through surfaces and explain all of the it's sort of the impact of variables on that heat flow, such as R value and U value and area and insulation levels and so forth. And then ultimately calculate a heating load um, through a surface and then calculate how much uh, energy would be needed, how many um, units of a given fuel source would be needed to provide that heat um, that space demands. Okay, so this is, as I think if you kind of take a step back and think about this, very practical set of principles and calculations here. I mean, this is really, really important. If you're designing a building, um, you actually perform a heating load calculation for the entire building, and then you can size your HVAC system and, basically make some sort of cost benefit analysis decisions. Do I, install a higher efficiency furnace? Do I maybe install a high efficiency heat pump? And so forth. And so this is really fundamental to building design because this is something that you think about it, you design and install this HVAC system. It has to be sized properly, and this is something that the customer is going to be dealing with for a very long time because once that system's in, you've already the capital is already kind of been spent, and so you really don't want to have to change that anytime soon. So this is a very, very important consideration. And then by extension, the cost of ownership of the building, and then we can look at the climate impacts, which we'll look at later in terms of carbon footprint and so forth. So very, very fundamental, very foundational. Okay, so hopefully that helps get you started, but make sure you go through all the content prior to lab on Wednesday. And then the other thing I want to point out is that in your lab folder, there is this overview video that'll, because we're going to be looking at construction drawings and of the F-wing, excuse me, the G-wing. Um, and so this will help you navigate that um, and will hopefully help lab go more quickly. Okay. All right. Well, if you have any questions, let me know, but I'll see you all on Wednesday. Have a great week until I see you.